So next we're going to talk about in-space propulsion. And some of these folks I see on the screen, I've also seen in the National Academy's Space Propulsion working group. They've been doing about once or twice a week for the past few weeks. And our moderator for this session is an old friend, Jim Reuter, our moderator from our last session. He didn't have to move, but we didn't give him time for a bathroom break either, I don't think. So sorry about that, Jim. But
oh, that's all
Jim
right.
has been the AA of STMD, acting AA for 15 months. And then since 2019, he's been the full AA. So Jim, go ahead and take it away with your panel.
Okay, thanks, Alan. I think this is an equally great panel. I'm really excited to hear the discussion on in-space electric propulsion. And the use of electric propulsion has increased significantly, as we all know, over the past 20 years, and is a major contributor for in-space propulsion now. It's what I would consider truly a transformative technology that applies over the entire range of small satellites to very large-scale interplanetary human exploration systems. So I'd like to ask you to join us for a discussion that includes electric propulsion leaders from NASA, academia, and industry to discuss activities that are on the forefront of electric propulsion. So I'd like to introduce the four panelists now. Dave Jacobson is currently the chief of the Electric Propulsion Systems branch at NASA Glenn Research Center and has over 20 years of experience and is a true research and development expert in this field. Andy Hoskins has worked at Aerojet Rocketdyne for over 30 years in engineering, program management, and business development, primarily focused on electric propulsion. He currently works in the Washington office supporting in-space propulsion and power. He has a master's degree in mechanical and aerospace engineering from Princeton. Jorge Delgado is a vice president at Apollo Fusion. He has over 13 years experience in the design and development of spaceflight hardware, including 10 years at Space Systems Loral, primarily focused on the development and production of Hall effect thruster subsystems. Jorge earned a BS in aerospace engineering from Penn State and an MS in aeronautics and astronautics from Purdue. And then Dr. Mitchell Walker is a well-esteemed professor of aerospace engineering and associate chair of graduate studies at Georgia Tech, where one of my daughters graduated, where he directs the High Power Electric Propulsion Laboratory. His primary research interests include both experimental and theoretical studies of advanced plasma propulsion concepts for spacecraft and fundamental plasma physics. Dr. Walker has authored more than 120 journal articles and conference papers in the field of electric propulsion and plasma physics and has received many, many awards. So I'll ask the panelists for opening remarks to try to keep them to 5 minutes, and then we'll have some topic discussion and open up for questions. So Dave, if you'd want to start us.
Sure, thanks, Jim. I'd like to give a brief history of electric propulsion accomplishments at NASA GRC and describe how the recent work that we've been conducting feeds forward to the work that we anticipate doing in the coming years. And while GRC works across a full range of electric propulsion technologies, my focus today will be on gridded ion thruster technology and Hall thrusters due to the community's level of interest in these topics. I'm also going to talk about EP support that GRC provides the rapidly expanding small spacecraft market as well. So if we can go to the first slide entitled 60 kilowatts, or excuse me, 60 years. I don't know if we're seeing that slide or not. So Lewis Research Center and now GRC has been conducting gridded ion thruster research and development for over 60 years, right? And so in and of itself is quite an accomplishment and a feat. My view of the period of time from the late 1950s to the early 1970s was one of very rapid progress, right? And so during this period, early mission analyses showed the benefit of electric propulsion and how compelling missions could be performed utilizing electric spacecraft. And really, that's what prompted the agency to make investments in large ground test facility infrastructure that is still used today. So if you see it on the bottom left-hand corner, some of the earliest facilities were very large chambers that were established at Glenn in 1961. So over a period of just 10 years, Harold Kaufman went from the invention of the electron bombardment ion engine to the first operational on-orbit flight of CERT-2, right? So that's really quite incredible and when you compare and contrast to the cycle of development time that we have today. So the mid-1970s through the mid-1990s was really a time period of intense research and development for this particular technology, focused primarily on 30-centimeter engines. And really what we saw during this time period was the development of modern dished optics, right? Ring cusp discharge chambers, enclosed keeper hollow cathode assemblies, and perhaps most importantly, the transition from metal propellants to inert gas propellants, right? And so all that's kind of segued into the 1997 demonstration of the NSTAR engine on Deep Space One, and then shortly thereafter, the utilization of the same technology on Dawn in 2007. So what I consider to be the modern era of gridded ion thruster propulsion started in 01, right? And that was with the initiation of the 7-kilowatt NEXT system ion propulsion development. Interestingly, the first flight units of that technology was recently completed by Aerojet Rocketdyne and delivered to APL for use on the DART mission just last month. So moving forward with this technology, GRC is collaborating with the U.S. Air Force on multiple approaches for increasing the thrust of power to make this technology more applicable to additional mission and get additional mission capture. Going on to the next slide. So the path taken to advance Hall thruster technology was very different. So I think many folks know this technology was advanced to a high degree of maturity in the former Soviet Union. And when opportunities for collaboration came about in the early 1990s, GRC was a key participant in those investigations of Hall thrusters that had been developed by a range of Russian institutes, including STMD and Fakal and Keldysh and others. But similar to gridded ion thruster technology, there was a rapid progression to flight demonstration, right? So by 1998, GRC integrated a combined US, Russian electric propulsion Hall thruster-based system and flew that on a Naval Research Laboratories spacecraft. And then shortly thereafter, conducted a flight experiment in 2001 to characterize plume impacts of a Hall thruster on orbit. So again, similar to the story I told with gridded ion engines, the period between 01 and 2010 was again an intense area of research and development. And during that time period, NASA evaluated Hall thrusters and designed Hall thrusters for NASA missions. And so we pushed forward with the power level, first to 10 kilowatts and later to 50 kilowatts. And we also advanced the specific impulse of these devices to perform NASA missions. And so a substantial portion of that work fed forward to the current development of the 12.5 kilowatt Hermes thruster, which is now being developed to flight readiness under the AEPS contract by Aerojet Rocketdyne. And so AEPS is a key element of a 50 kilowatt EP system that will be flown on PPE. And that will serve as a stepping stone for more ambitious missions such as Mars exploration. Moving on to my last slide. So, you know, we've talked a lot about particular technologies. This is a different flavor in that this is low power electric propulsion, right? And so low power electric propulsion is applicable to small spacecraft, and it's really seeing a lot of interest. We're seeing a lot of interest in this sector, and so NASA Glenn has been supportive in a lot of ways, right? We've been conducting independent verification and validation of industry-developed components and systems. So this is unique in that I talked about the work that we've done developing technologies. This is a case where NASA is evaluating others' technology and trying to assist them by using our infrastructure and applying it for those purposes. We've been conducting non-exclusive, no-fee licensing of NASA-developed technology with a current focus on low-power Hall thruster technology. We're collaborating across the board with academia, other NASA flight centers, industry users, and other government agencies. As you can see some examples there. And we're seeking to promote engineering rigor in this area where establishing guidelines for certain aspects that we think are important. And lastly, we are providing SMEs, subject matter experts, to multiple mission directorates for the programs that both SMD and STMD administer. So with that, I'm gonna turn it over to the next speaker.
Yeah, thanks, Dave. It's fascinating to me the very broad range of applications that we're seeing for electric propulsion. Andy, do you want to go next?
Sure, absolutely. So, you know, from the moment I walked into a lab in September of 1986, into a lab labeled electric propulsion, having no idea that the technology even existed till today, I've had a chance to work on 5 different EP technologies, ranging in power from 70 watts to 26 kilowatts. And seen EP kind of go from something that was just completely lab devices to you know, a mainstay of spacecraft subsystems. So I want to take a couple minutes to kind of add on to what Dave just went through, give kind of an industrial perspective of, you know, of the markets, and, you know, say a few words on some of the developments at the high power level. So the slide that says operational EP spacecraft, which is the second slide there. 25 years ago, EP was starting to be used commercially, primarily for station keeping and GEO. More recently, we've seen a dramatic expansion of the use of EP, especially in GEO, seen in the you know, the 2018 chart on this. You know, every GEO platform today offers an EP option, and many of them offer all electric options where they'll completely eliminate the chemical propulsion you know, system. But go to the next slide. So we've been updating our database of every satellite that ever flew EP. This is slide 3. This chart is a chart of cumulative number of EP satellites since 1964, the first launch of any EP at all. What you see is an absolute explosion, especially in the last 18 months, with hundreds of Starlink and dozens of OneWeb satellites that have been launched, each with a Hall thruster. You know, nearly 1,300 EP satellites. The startling figure that speaks to the absolute widespread acceptance and even commoditization of electric propulsion, especially now in LEO. But the market is pretty complex, and so go to the next slide, which slide 4. So when we discuss the EP markets, we often break them down into power per string, you know, EP thruster. Power per string is related to power per spacecraft, and that's roughly tied to spacecraft mass. So the market dynamics turn out to be pretty different between each of these different segments. Of course, the breakpoints are approximate and there's overlap, but these are reasonable, you know, categorizations that might be useful for our later discussion. In the case of medium power, that's where EP first gained its real foothold, primarily with GEO, starting with station keeping and then moving to orbit raising and orbit acquisition. You know, it's a mature market. I mean, the key thing there is it's a mature market. Price is a factor, but the big issue right now is that the number of GEOs being ordered per year has declined pretty significantly over the last 5 years. So where do you look for the next big thing? So you could look at, you know, low power, which I'm defining as 100 watts to a kilowatt per thruster string. And this is where we've seen the huge numbers of spacecraft both being proposed and now fielded. Challenge is that the price points here are extremely aggressive, and but we've seen a lot of innovation here, and I think Jorge will actually speak to that to some degree here. Then if you go to very low power, price sensitivity is even more extreme. There are more entrants and new customers, including for the first time really academic customers. And then going in the other direction at high power, there's a completely different market, and it's another, you know, emerging market. Basically, these are logistics markets built around the desire for NASA and DoD to move a lot of stuff around. These are missions that wouldn't have even been feasible a few years ago. So let me just finish by, you know, noting a couple areas where NASA and AR have been working together. Dave's already touched on them, so I'm just going to touch on them very briefly. The next slide, slide 5. NextC, as David said, you know, despite COVID shutdown, we were actually able to deliver the first thruster and PPU for NextC. NextC is particularly good for very high delta V missions, especially NASA science missions that are enabled by something with the kind of total impulse that Next.
Have we lost Andy?
I don't hear him, Jim.
Okay, but okay, all right. Well, all right. Well, I think Andy was wrapping up. So next, why don't we go to Jorge?
Hey, thanks, Jim. And really, I mean, thanks for the organizers of the symposium and for having me on. Very honored and nice. Hopefully Andy makes it back. All right, we're gonna fly blind. So I'm on a chart titled Novel Spacecraft Tech to Commodity Product. And that's, really what we're saying is, I think we could say, electric propulsion is mission enabling, and it's almost cliche now. But it's been spread across the entire market from large spacecraft to small spacecraft. And it's been done in a short amount of time. And I know we talk about, Hall thrusters being introduced in the US in the early 90s and ion engines in the 60s. But like one thing I always like to make clear to folks is, the first all-electric GEO commercial sat launched in 2015. It's 2020 today, so it's only been 5 years. And so it's a mature product, but it's also definitely still in its infancy. And now it's enabling these small satellites, which everybody speaks about. And how does it enable these missions? Well, it enables you to really load up your launch vehicle, right? So on your launch vehicle, you're going to be limited by mass or by volume. And what EP allows you to do is really bring those two together. So if you can fill up that fairing and not leave it, any performance on the ground, you can fill up your constellation faster. And that's really what EP is doing. I mean, just from a very high level. And then beyond that, we have the small, like even smaller sats, which I'll classify as less than 100 kilograms separated mass, using micropropulsion, which is really exciting, and just opening up Delta V missions, which I don't think anybody really could have thought about 15 years ago. I think I'm the youngest guy in the panel here, but when I came out and started the industry. And so what's going on now is we got big birds want it, small birds want it, even little itty bitty birds want it. And so it's just a basic demand curve. It's pushing the price down, as Andy hinted at. And, it's pushing the price down so much that you can have, venture-backed startups like the company I work for here in Silicon Valley working to really, design every last dollar out of these units. And we're seeing a transition from, research and exquisite hardware to low-cost, high-volume production. What are the basic requirements? I have thermal requirements, obviously thruster and ISP. I got to survive a dynamics environment. Okay, what can I rip out bare bones to make a thruster, to make a PPU? So that's what we're seeing right now within the startups, and even with the larger companies. I think Andy could talk about it as well. And then what we're seeing is competition increasing. First domestically, because as Dave pointed out earlier, the incumbents are from Russia, and we're the ones coming in. And so domestically, you're seeing many companies pop up, and internationally as well, especially in Europe and even in Asia. So now we're on a chart titled Trends in Electric Propulsion. So just a couple things I can mention here. So one, what are we seeing in the last 2 years, 1.5, 2 years? Small spacecraft and their missions are getting bigger, right? So you have a communications spacecraft and you want to launch it. Well, the revenue you generate from that communications spacecraft is based on the amount of energy you can put on the ground. The amount of energy you put on the ground is based on your payload power. Your payload power means your spacecraft's bigger. Your spacecraft's bigger, you need more total impulse. You need more total impulse. The thrusters may get bigger. The propellant tanks may get bigger. And that's what we're seeing. And you're even then going to higher altitudes to have a more efficient put down efficiency with your payload. That means using more EP to get up to those higher altitudes, maybe going up a little bit higher power. Now you start seeing maybe a spacecraft is going to size its power system for propulsion, which is like, it's been my dream since I was in school. And so we're seeing this trend here. Also seeing is spacecraft primes, they want ready to integrate subsystems. So they really want to push a lot of their costs down to, not just the thruster manufacturers, but I think a thruster manufacturer has to be a system manufacturer. Now I'm creating a subsystem, integrating it on a panel and giving it to you, and you just bolt it on your spacecraft. And you're seeing that a lot more and more now in these proposals where the total cost of system integration is being pushed down the supply chain. Then there's propellants. And I think everybody always talks about propellants. Constellations, they like Krypton. They like Krypton, well, because it costs less. And so if you're going to put up hundreds of spacecraft, you're going to load a lot of propellant. The money will trump your trade regardless of what you're looking at. But others still like Xenon. If you just have a small number of spacecraft you're trying to put up, and you're very volume limited, the compressibility of xenon still works. And I've seen government and civil space still like xenon. So there's still a tussle there with the two. And then I got a little blatant advertisement there, some Apollo hardware running both propellants. And then lastly, what I'll say is, the thruster is easy, and I got to qualify there with the parentheses, but it's not that the thruster is easy. Everybody knows, what we're doing is some pretty difficult science, and taking a unit that reliably activates and runs in a lab and ruggedizing it such that it'll survive the space environment. Equally as important, because the thruster is not going to run if one of those other two guys isn't running. So, I got like my little message there is PBUs wanted. These are just some snapshots of PBUs that I've worked on in the past. And they're from open source papers that I released. So I forgot to put footnotes there. So I was really happy to see in the previous panel, the gentleman from Moog discussing discharge converters and seeing work being done there. Because I will say that, folks in Europe started investing heavily into PBUs in the mid-2000s, late 2000s, whereas we didn't see an equivalent effort on the power processing here in the US until more recently. And so what you're seeing is everyone's trying to catch up. So there needs to be a lot more focus on the PBUs, and then also the propellant management for these systems. So if the cost is being pushed down the supply chain, and to put together a thruster and a PPU and a propellant feed system, what we're seeing is an equivalent cost driver on the feed system. So pneumatic valves and regulators, which are historically expensive and heavy, people are re-engineering these, trying to get them down as small as possible, which is overall driving this trend to be able to, just package these systems in low volume sub-assemblies that can be put out in mass quantities, further reducing the price, making spacecraft primes very aggressive in their swap analysis, or you could swap plus dollar analysis. So that's all I have to say right now.
All right, thanks so much, Jorge. I'll definitely put a plug in also the PPU work, especially as we're trying to grow our systems to go to humans to Mars, is a really critical area for us to be addressing. So now I'd like to turn it over to Dr. Walker. Mitch?
Sure. Once again, thank you for the opportunity to speak. Distinguished panel members, I look forward to having a good discussion with them. In a short amount of time, I want to talk about why we're here. There's been a unique movement in our market. We have low-cost launch vehicles, we have small satellites, we have small, cheap electronics, and we have a demand for service on the ground. And so that's really been a pull on what's going on. And so if I could leave you with one word here, I would say it's growth. Electric propulsion in that community is still in a growth phase, and we're all trying to adapt to it. I'm going to ask you to go to slide 2. All right. You there? Perfect. So as a university professor, one of the things I'm always thinking about is where are we going to place these students? And if we look back in 2005 and even 2010, there were 3 or 4 companies on the market. They sold a subset of products to feed these spacecraft, and that was it. And then along came the venture capital and the small satellites and all the other pulls. And now you have a plethora of electric propulsion houses. And these are established places. These are great people. They're all qualified. They have real missions. They're moving forward. And now the university, and many of the university programs, we're all trying to fill these programs with good, talented people. And so you'll look around the country and you'll see that a lot of the research programs are beginning to repopulate, reinvest, because the demand is there for the students. The pull, of course, for the technology, as people have mentioned, is on both ends. The small stuff, more for the constellations, and then the bigger stuff that NASA is doing. So I'm going to stop there, and I look forward to the discussion.
All right, thank you, Mitch. Growth in this area is definitely a key factor, and that we're seeing. So then what we'll go is to topic. First topic that I'd like to have the panel discuss is to discuss the biggest challenge you see in advancing the in-space electric propulsion field, including any international competition considerations. And I'd like to, Andy, as I understand it, you're back. So I'd like to start with you and give you an opportunity to give a final thought on your opening if you want.
You know, actually, it just sort of dovetails with where I was at with the charts, and there's sort of two things. One is at the high power end, a big challenge, and I think if people sat through the lunch break tour of the EP labs, they could see the size of the facilities there, and that's for sort of state of the art right now. But one of the big challenges is doing ground-based testing as we push up in higher powers. The other is that there is, and this was just alluded to as well, a lot of investment overseas by the Europeans, the Russians, now actually the Chinese in electric propulsion. So there's a lot of overseas competition for us on this.
Okay, thanks, Andy. Jorge, do you want to add to it?
Sure. I mean, I think the biggest challenge is maybe the last bullet I mentioned is, PPUs specifically, and we're driving powers down and trying to make things at a very cost-effective price unit, really trying to reduce the cost of the overall system. Historically, PPUs are the most expensive part of the system. I think we're seeing maybe a possible transition there, but if you want to build a reliable unit, you still need to meet specific radiation requirements, thermal requirements, and so now we're talking about piece parts, and you start playing with GaN devices and silicon devices, and so it's being able to find all of the right parts that you can properly test, meet all your requirements, and get it done. And so I think that's where there needs to be maybe some more investment in whether it be from NASA or government agencies on making available high reliability parts that can be mass produced at low cost, that could go into these units and be put out into the market.
Okay, thanks, Jorge. Mitch, do you want to?
Absolutely. So biggest challenges. I'm gonna take two, since you can't stop me. First one is
two is this fine.
on the high end is related to lifetime. At this point, we have engines that run 13,000 hours. And our next batch of big missions, especially for NASA, we're looking at 20,000 hours, 50,000 hours on an engine. And that's hard, right? You're talking multiple years for the engine to survive. I'm not convinced that we are going to sit on the ground and watch these engines run for 5 years to see if they're going to make the full life. So instead, what we're going to do some combination of small life tests combined with a really good model, and we'll take those life tests and we're going to anchor that model, right? And that's how we're going to get to an answer. And the challenge is right now, do we have the facilities to give me 5,000 good hours on a really high power engine, so then I can anchor that model out to 50,000 years? So that's the biggest challenge, number one, life and the facilities required to address it. Second biggest challenge is related to how we've been building thrusters. And it's coming out now in terms of manufacturing processes and material processes. So historically, we go in a lab, we build a wonderful thruster, amazing performance. And then we would just try to take that design to qual, right? On the small side, that doesn't work because that might not be the cheapest way to build that device. And on the big side, we're starting to bump up against material issues and manufacturing issues because we're taking the lab approach and trying to qualify it. So I think there's a lot of opportunity to deal with the challenge of the design and the materials and manufacturing we've been approaching the problem with. I'll stop there.
All right, thanks, Mitch. I definitely can relate to that, the concern on testing ability and the modeling that goes with that. And then Dave, do you want to wrap up this topic?
Yeah, yeah, sure. I think those were all absolutely key challenges that we're facing in electric propulsion. I agree with all of them. I think I'll take a different angle at it, right? So, we talked a lot about how electric propulsion is really advancing and how things have changed in the past 20 years, and we're seeing more and more spacecraft flowing with electric propulsion and so on and so forth, right? And that's all true. I do still see room for improvement, and when I look at it, I still don't see us being over the hump, if you will, right? And absolutely, SpaceX has been incredibly successful, and OneWeb and whatnot, and it's so wonderful to see the proliferation of these devices being flown. when I look at it, though, I still see very few qualified devices that can be used for NASA missions. And so I think that's a real challenge. And I think that a couple things that we need to do is, one, we need to stop chasing performance and new concepts without qualifying something that can be used, right? And that we can then improve upon. That's something that other countries do really well, and we haven't had similar success. And I think Jorge obviously it represents a new start in the industry, and that's incredible, and we're hoping to see more of that. But I think seeing more expansion of the U.S. industrial base and more products is really what's needed in this area. More qualified products that can be used.
All right. Thanks, Dave. Why don't we stick with you for the second topic question then? Is can you discuss what you see as overarching trend or the next step to advance the in-space propulsion, in-space electric propulsion field?
Yeah, well, certainly in the near term, our primary focus, or one of our primary focuses, is to see through the flight of a very high power EP system, right, at a much higher power level than has been used historically on PPE, right, and as you know very well. Beyond that, what we're very hopeful for, and this has been discussed now for the past 60 years, which is the use of electric propulsion to go to Mars. And so we're very hopeful that we have the opportunity to work at higher single unit power levels. And certainly I acknowledge some of the issues that have been discussed, such as facility considerations to do that work. But I do think, right on the heels of demonstrating a 12.5 kilowatt system and a vehicle level power level of 50 kilowatts into the EP system, I think the trend is toward going to even higher power levels to perform Mars exploration.
Okay, thanks. Mitch, do you want to add to that?
Sure, just a few comments. Absolutely, the power systems are becoming more impressive. They're becoming higher power to mass, and that's going to do a lot of things for electric propulsion. So really, the EP community, as always, is following the power systems.
Okay, thanks. Andy, do you want to add?
Yeah, as you go up in power, I think you're going to get to a point in terms of power per thruster where you're effectively not going to qualify it on the ground like you do, and there's sort of a knee in the curve, and you're going to end up flying a demo without a traditional, conventional sort of ground test type of a thing, because it's just going to get to be too big. The other thing that is out there that I don't necessarily know that people have focused on a lot is some of the electronics components for dealing with the very high powers. You're going to end up, if you just use MOSFET, what we feed off of what EEE components are available, on the market. And those are typically not, trying to deal with, 100 kilowatts of power or something like that. So you'll end up with 50 zillion, MOSFETs, for example. And the availability of components like that are going to end up being, a development issue.
Okay, thanks, Andy. And Jorge, do you want to add to this topic?
Yeah, I mean, I think I mostly agree with what is said. But I will say, I mean, yeah, you're going to go up in power and you're going to run into the parts issue that Andy's talking about. And a comment I always like to tell my team here and previous teams at OneWeb and SSL is, the hardware that's there wins. And so if you have a product that's flight proven, qualified, and you show it to folks, missions will adapt. When I was at SSL, I was part of the proposal team for the Psyche mission that's using commercial EP to go to Mars. And I think at some point, yeah, we do want to push forward and we want to have these missions, interplanetary missions. And there is hardware today that could be used if the missions are altered or adjusted to be able to take advantage of the hardware that's there.
Okay, thanks much. I think now we have a couple of questions from the audience. So Jim Way, do you have a question for us?
Yeah, absolutely. Thanks, Jim. So our first question actually is going right back to Mr. Delgado, and it comes from Al Tadros. Yeah.
Hi, Al.
Now you start. Can you talk about where innovation is heading on the smaller end of EP, basically less than 1 kilowatt? Are there more efficiencies, innovations, or propellant types that aren't feasible for larger EP systems?
Yeah, I mean, I think, when you, like I said, you start getting into this 50 kilogram range, you're really power limited, right? I mean, your spacecraft separated mass is, somewhat linear with the power available. And so you start looking at, there's companies out there, Axion and Propulsion, building up electrosprays. I think they look promising. I think, when you start growing that and seeing if you can put them on larger birds to get higher delta Vs for, say, 200 kilograms, 300 kilograms, 500 kilograms, you start, having questions about life and how they're actually going to perform. And so it's somewhat difficult to scale by mass chunks. I like to put everything in chunks of separated mass. And I think there's definitely technologies that work well, sub 100 kilogram separated mass. And then it's kind of difficult to stretch them out beyond that. And then what we've seen Hull thrusters do very well, anywhere from 150 up to, I'd almost call it like 1.5 to 2 metric tons. And then that's where you really start competing well with ion engines, and because ion engines, just the higher ISP, then it's a toss-up on the type of mission you have. Do you have a comm mission where you have to get there fast? Do you have a science mission where you get there slow? And that's really the trade between the Hull and ion engines. But again, the Hull thrusters, once you start pushing the power way down, those it wants to be at a higher power density, and it's tough to really push it down below 100 watts and have a reliable unit. And then as you start growing power, I think, you can get to where you want to be if you can find the hardware to run it, the piece parts and the PBUs that can handle the power levels. And so I think there is some promise on the electrospray side, maybe some years out and some more development away from getting there. But I guess that's kind of what I'd say. I hope I answered your question, Al.
Excellent, thanks. So another question from another attendee. What mature or more developed industry is similar to EP, the EP industry, and can the EP industry learn from that? So what parallels are you seeing out there that the EP segment might be able to take from?
Does someone want to answer or take a cut at that? Dave?
So if I understand the question, the question is utilizing another industry as a model for the electric propulsion field. Is that the genesis of the question?
Yeah, pretty much. It's maybe a more mature or developed industry that's really similar to electric propulsion, and
yeah,
you can learn from that.
So I think about that often, and I sometimes I think, I look to the chem propulsion area and follow the historical trend from the Apollo era to the current state, where you had proliferation of number of companies and devices and whatnot, and then obviously a lot of consolidation that's occurred now to where we are today. And so I don't really know if that's what's going on or something that we would want to model or not. I don't necessarily think so. I think what might be a better way to look at it is how could we use the best practices and commercial approaches for certain aspects of electric propulsion, like within power processing units or certain aspects of thrusters, so that we're not reinventing the wheel all the time. I've long held the belief that we make power electronics and power processing units too difficult. They're one-off. They're built for a very specific purpose and system, and so I think there's opportunities there to do things differently and look to other industries and look for those best practices. Although I can't sit here and tell you exactly what they are, because obviously, if I could, I would be doing really well, and I'm not. So
I'll take a stab. I think it's a little bit of a head scratcher. Maybe it kind of shows how we put our little niche technology on a pedestal here. But, I'll say, electric vehicles. I think in electric vehicles, the powertrain and the drivetrain is there. And now they're really tackling the power source, right? And I think that's somewhat of what you're seeing in EP. Obviously, they're moving a lot faster. They only have terrestrial requirements. But I think that's an industry that's, again, pushing, FET technology, piece part technology that could eventually go into PBUs that we could use. And it's something that, I think maybe more folks in our community should follow a little more closely on what they're doing power electronics wise in the EV community.
Yeah, I think that's a good, good, Andy.
Yeah, sorry. I think that one of the huge challenges that we have is that even with the high rates that we're talking about right now, the rate of, the rate of production is still in the dozens per year at a very high level. And for the high power stuff, it's, single units per, multiple years. So a lot of times I think that one of the things that gets done is people apply things that are associated with high rate production type things, because that's what most manufacturing is. And that's what, you pick up an Inc. magazine or whatever, and it's about high rate production. And we are dealing with things which are, at the low power end are sort of high, but they're still, they make commercial aircraft production look high rate. I'd say that might be something that we could, look toward in terms of, if you're talking about at the low power end and you're talking about building sort of an assembly line type of a thing. But I think that the other side of it, when we're at the high end and we don't have a lot of units, I think that one of the things that I really strongly feel that actually the Japanese have done a good job at is not over specializing, having small, flat teams. And that has seemed to work very well, because there's fewer communications, fewer people, fewer nodes. And I think there's some theoretical, things that say you'll have less cost and less likelihood for miscommunication, which is where a mistake creeps in.
All right, thank you. Jim, do you have any other questions?
Yeah, I've got a couple more. Let's see. So we talked about the humans to Mars. How will we make a decision on nuclear, thermal versus electric for when we venture out there? Yeah,
I suspect I should probably try to take a cut at answering that one, unless somebody wants to volunteer. What I'd say is, what we're right now is we're building the Artemis mission and developing our plans. We have we keep a strong eye towards how do we get to Mars with humans. That's our ultimate goal as we're doing this. A sustainable presence on the moon and then on to Mars. And we're looking really hard right now as an agency is what would be the critical technologies that we'd want to work on to develop so that we can enable a Mars mission sometime probably in the 2030s. What it leads to is if we really want to enable opposition class missions or something that really greatly shortens the time, at least on the round trip, then it really points to a nuclear solution. And as the person asking the question alluded to, we're looking really hard at both nuclear electric and nuclear thermal propulsion systems right now. And what we have is architectural studies going on of how best that we can enable and what how best we can enable the mission and what are the critical technologies that are needed to get there. And so those studies are going on. What we have done ourselves is we've had sanctioned an NESC study within NASA and with broad expertise from the outside that looked at and assessed the critical technologies between nuclear electric and nuclear thermal propulsion, and especially with related to how could we enable a flight mission by the mid-2030s. We also have now a National Academy study that's going on and will report out in the spring timeframe on their assessment of these two technologies. So we have the architectural studies going on, and if they point towards a clear favorite, then we would probably make the decision sooner rather than later, which would be probably in the measured in weeks. If it looks like it's going to be a close call, we'd probably want to do some more technology development work before we get into them, and so it could be months. But really, in this this next time frame, when we're reading next year, we would expect that we've largely addressed the questions, and we may or may not have finalized a decision, but we're much farther along.
Excellent. Thank you, Jim. Let's see. Is electric propulsion a candidate for mandatory deorbit capabilities? Talking about space debris.
Absolutely.
Yeah.
Yeah. Jim, can I take something on that?
Yes.
So, yeah, so we've actually been doing some work looking at some mission analysis on that. And when you're looking at mandatory deorbit, you're trying to impose, you're potentially imposing, a mass penalty on someone. And the mass penalties get to be, in the 10 to 20% potentially, depending upon where you're coming from for chemical propulsion, but it can be under 5% if you're talking about an electric propulsion system. So it is not only a candidate, but it may actually be enabling if we get to a point where we're looking at mandatory deorbit type things, especially when we're talking about these very, very large constellations, which are obviously, something of an issue. And people should understand that, above about 650 kilometers, the deorbit times are far longer than the 25-year type, requirement. So, you could be talking about, a large proliferation, in that region. So yes, the end result is yes.
Thank you.
Yeah, I mean, I'll agree. I think beyond maybe even just the big constellations, small Earth observation spacecraft that would typically stay away from propulsion are going and looking at small EP systems because of, a concern of what the regulatory agencies may impose on them by the time they're ready to launch. And then from there, it's like, okay, well, if you're putting electric propulsion on, then how can we, enhance your mission even more beyond just giving you a deorbit, solution. So
yeah.
Great, thanks. Let's see, we do have a couple more. What are potential cooperation perspectives, both domestically and internationally, on development of these systems? Don't all answer at once.
Do you want to try to think? Yeah.
I feel like I'm talking too much.
Yeah, go for it. All right.
I mean, I've done quite a bit of international work within the EP community. I mean, it's how I started. I did quite a bit of work in Russia with the previous company I was with, and in France. And I think the EP community globally is great. We're just full of very smart, eager people. And there's definitely opportunities to collaborate. I think there's some great work on the power electronics going on in Europe. The Airbuses and Thalases are just building some really good products. And then, there's great work thruster-wise here domestically and in Russia and in Europe as well. And then beyond just the EP community, it's what folks are doing in Japan with power systems, here in the U.S. and in Europe. I think there's definitely opportunities where, if the mission so calls for it, to really bring parties together and put together some really neat systems.
Yeah, and some of the changes to ITAR have opened up, made things a little bit easier for cooperation, especially at the lower powers in recent years. Below a certain level, the ITAR limits are something which are, for example, for Apollo fusion level type things, for example, the low power EP is a lot more open.
All right, great. Just speaking of the partnerships, so is there any particular type of model or different model of public-private or other that would make high power electric propulsion that really doesn't have a broad base of users beyond NASA viable for long term? So something that's got some longevity to it. So is there a different model for that kind of a partnership in the industry?
Yeah, I don't know if you want to take that, Jim, or not. I'd be happy to share some thoughts.
Go for
I
it,
think,
Dave.
yeah, I mean, I think STMD is, I offered it to you because I don't want to speak for STMD necessarily, but
That's
you know,
fine.
STMD is very interested in that, right? You see that in the different mechanisms that they are using to do the portfolio work that they have, right? With ACOs and tipping points, and so I do think for a device that doesn't have broad commercial use, that some alternate model to what historically has been done for those developments could potentially be at play. And as I said, the agency is moving towards being receptive to alternate mechanisms. What exactly that looks like, I don't know. But it certainly would depend on a lot of things, including the previous question asked about which technology is selected, right? It would certainly depend on that as well. So, but I do think it's a very good question, and certainly one that we're considering in the context of how this development is done.
Okay, great.
Yeah, thanks, Dave.
thanks.
Go ahead, Jim.
Yeah, sorry. And so this one might be directed towards Dr. Walker. It comes from a student attendee. So how would you recommend a mechanical engineering student get a good foundation of skill sets if they're interested in getting involved with electric propulsion? Should they be really specialized in the specific physics fields of these systems, or is a more generalized mechanical focus better for them?
Sure. Of course, I'm going to recommend aerospace engineering, but I'm slightly biased. So to do well in this field, you want to have some knowledge of a propulsion course. It'd be great if you had a couple of electrical engineering courses and then a couple courses in plasma physics / nuclear engineering, and that would give you a good start. This field is very hands-on, so if you had any chances to do undergrad research or some of the design, build, fly activities, or some of the SAE activities with Baja car or Formula One car, those would all be excellent ways to get a background to get started. And then, of course, if you had an internship related to electric propulsion, that would really cap things off. Great question.
Great. And then I think I've got kind of one more that could be an interesting response from everybody. For each panelist, what is your dream flagship mission for next generation electric propulsion? Again, don't all start at once.
You want a galactic cruiser, right? I mean, we all grew up watching Star Trek. That's why I'm here, right? TIE fighter is a twin ion engine fighter. No, all joking aside, I think I want to see more interplanetary. I want to see that pushed. I think everybody that's in the aerospace industry is here because they want to work on interesting and neat projects, right? And you keep pushing the limit. And I mean, the reason I'm here is because I walked into the lab when I was 19 and I saw some guys twiddling around with a little arc jet with a plasma, and I said, wow, that looks like science fiction. I want to work on that. And so here I am. And I think, using these technologies to go to Mars, go to Venus, go beyond that, any one of those missions, I think I'd be honored to work on, right? That's why I'm doing what I'm doing. I used to tell myself when working on large commercial spacecraft is, we're never going to have some kind of Battlestar cruiser if we can't run DirecTV for 15 years without an issue, right? So, baby steps, but eventually, just larger interplanetary missions. I'd love to see all that.
Yeah,
So
I have to admit. Go for it there, Dave.
Go ahead, Andy.
I said, I have to admit I was disappointed when Dragonfly won and Caesar lost, the Comet sample return. I love the sample return missions. They're great missions for EP because they're ambitious. They're difficult to do otherwise. So For me,
Yeah,
it would be that kind of a thing at a power level that I'm going to see within my lifetime or my working lifetime too. That's the other thing.
Yeah, I would certainly agree with that. We would at Glenn Research Center love to see Next utilized to its full capability in any capacity, right? Whether that be a common service sample return or whatever. So when I hear flagship, I think science, but for me the dream mission would be to see some very large nuclear powered spacecraft going to Mars, right? I mean that when I think that I would die working because that's something that I think anyone in this field would want to be a part of.
Yeah.
I'll just add a little bit to that. Would love to see us have, enough power that it gets really interesting. I think it's interesting for where we can go, what we can do, and having devices, not where we've got 57 of them to process the megawatt, but where you've got, one, maybe two engines that can do it, and they're small and dense. That's where I'd like to go.
Mm-hmm.
Very cool. I think we've gotten through the questions, and we'll kind of wrap up now. And what I'd like to do is do the lightning round question for each of you real quickly, no more than a sentence. And that is, what's keeping you up at night? And we'll just go down the order that we started with. Dave?
I mean, it's simple for me. PPE keeps me up at night, right? It's probably the most important thing that our organization has worked on, perhaps ever from my perspective, and seeing that to its success is extremely important to me personally and to a lot of people at our center, and so it certainly keeps me up at night, every aspect of it.
All right, I love your definition of one sentence, but that's great, Dave. Andy?
I just have two words: cost reduction. Keeps me up.
All right, thanks. Great. Jorge, I think that balances out then. Jorge?
I'd say, available power levels that are out there, and whether we're, is it shifting around, too much?
All right, and Mitch, why don't you wrap us up?
How do we predict on-orbit performance from the facilities we have?
Great. All right, well, I think with that, we'll wrap it up. I really enjoyed this panel. It was very insightful for me. I think the questions were great and numerous, and I loved the responses. So Jim, I'll turn it over to you. I think we can declare success.